So it is a pleasure to have Professor Sivakumar from the University of Hyderabad, School of Physics, University of Hyderabad. So presently he is an honorary professor there, and in fact he was a lecturer. He joined as a lecturer in University of Hyderabad in 1990. Retired in 2021.
Hey, hello, excuse me.
His main research interests are in quantum physics, cosmology, and theoretical particle physics, and he has a number of research papers linked. And presently, he was also an associate of ICTP, and he's also a fellow of Andhra Pradesh Academy of Sciences and Telangana Academy of Sciences. And presently, he's also interested in the teaching of physics. So he's associated. He's the main coordinator of the physics teaching and talent search program. And so today he shall be talking on how effective field theory is. So
yeah, I think can you hear me? Possibly from Google Meet I can hear. I think there's a problem with the audio. Battery is weak. Yeah, first at the outset, it's a very pleasure to be back to Essenberg Center, and I'm very happy and thank Amitabh Lagari and Sundara for inviting me. And I should tell you that I am one of the first person to get selected here, along with Robin Banerjee, professor, and myself. We were the first postdoc to be selected as in the Essenberg Center. In fact, I recall, the whole historic. Many of you may not even know. In DB17, there used to be a 3-bedroom apartments. I mean, 3-room apartment. The ground floor where when all the postdocs and people were staying. And that was a very kind of prehistoric of Essenberg Center. So it's like homecoming for me in that sense. So I'm very happy that that small center, which was just in a 2-bedroom, 2-floor apartment, has now grown into such a big center. Okay. So, first at outset, my title is How Effective Field Theory is. I just want to make the pun on the word effective before I'm putting the word comma there. Right? So sometimes, it's bad to explain jokes. that's defeats the purpose of the joke. And I should also apologize that RTSP is meant for somewhere else. I could not, send the actual file which I prepared for this talk. Giving the post center as a thing. So, so before I go into the topic of actually field theory, we should even keep in mind what are the scope of generally a physical theory is supposed to mean. For that matter, even science is supposed to do. God facets of a science is it should explain why things are the way they are. If you see, eclipse, or if you see any of the astronomical or terrestrial phenomena, that's something people in those days were always wondering why things are the way they are, why they are happening. Then people used to give theories. Those theories was put in about a mathematical format. Then it has to be expanded, and it should give a prediction. It should explain what is already known. It should make new predictions. The new prediction must agree. Okay. Therefore, it has several things. First is a broad principle. Then there should be a mathematical framework. Then that should explain what is already known. It should make a new predictions. And ideally, a good physical theory should explain a maximal number of phenomena with a minimal number of principles. If you say for each phenomenon I'm going to introduce something, then that is much less taken than something which explains many things at a more general thing. So, so with this broad framework, we all know that the basic thing, those started from Aristotle and everyone, this framework in that physical theory was completed by Newton. It was taken over from Tycho Brahe, Galileo, and others. And we had Newton's laws of mechanics. Right? And the first thing, Newton had 2 contributions. One is his Newton's laws of mechanics, and then his universal law of gravitation. When he combines both of them, it was a very stupendous success. And the concept of force was just introduced. But the force, one always meant a contact force. By a contact force, what one means is if I take an object, if I give a push, that object touches the other object. If I give a push, then it undergoes a force and there is an acceleration. That is an action, that is a contact force. We expect all the phenomena must happen with that contact force. Suppose that did not happen, right? I take my hand and push something, and objects here, they start moving, right? With nothing in between, we would regard it a very startling, or I may become a godman and become very rich. Okay, all these things can happen, but then we would think that that is not physics, right? But so that is not what you expect a science to do. But then, if you look at Newton's law of gravitation, what does it do? It says there is a force between two objects, say for example, sun and the earth, and sun exerts a force on gravity on earth. But what is there in between? Nothing. There is no contact at all. But still, it sort of exists in that. Okay? Then somebody with that kind of a thing and say that isn't it an action at a distance? When nothing in between them, there is a force of attraction between them. And this was something which was people at that period were worried about it. But then Newton's was so successful, they could not find it a big major thing in accepting that. But Newton, when Newton, he was aware of these deficiencies. In fact, in one of the letters which he wrote to his very close friend, one body may act upon another at a distance through a vacuum without the mediation of anything else is to me a great absurdity that I believe no man who has in philosophical matters a competent faculty of ever falling into it. Gravity must be caused by an agent constantly according to certain laws. Right? He has not even told what the laws are. He didn't even say it is his laws. Right? According to certain laws. But whether this agent be material or immaterial, I have left it to the consideration of readers. If you see, is it my proximity? This, the material means, what he meant was something which is like a material objects, right? Like a contact force, right? That's what he meant. Or it can be even without that also. He has kept that open, right? Newton being Newton, one can see that he is sort of far ahead of time to even say that, he could understand the limitations of the current knowledge. What can happen in future? He said, I will left it to the consideration of readers. I'm sure by readers you would have meant some people like you and me after 500 generations and centuries much later, right, rather than his own readers of the book. Now we have got a similar situation in electromagnetism. Right? There also we have two charges where there is no medium between them. They exert force on each other. Two current carrying conductors exert the force on each other without any medium. That was also initially was very surprising. But in the electrodynamics, historical evolution is a very fascinating subject, because initially people thought that there was an ether as a medium was there, and the forces between these, all the electromagnetic forces, Coulomb's law, Ampere's, all of them was caused by a mechanical stress and strain. They thought there was a ether medium, it has a lot of nuts and bolts, vortices and things like that, and that is what caused these things. Because you see, parallelly at the same time, hydrodynamics was equally well developed. Helmholtz and others were developing. So many ideas from fluid mechanics was borrowed. Vortices and all was there known. Before he thought, yeah, either had vortices in it. So this concept was there. Then they were trying to implement in this. And this mechanical model of ether was being pursued quite vigorously. But Faraday was the first person to Faraday was the first person who tried to give the lines of forces as a kind of a geometrical reality for it, because he is not a mathematical physicist, here, and he wanted to understand everything through some pictures. Therefore, through these pictures, he wanted to bring. And this Faraday, I think, remember, Faraday was the first to even coin the word field. Certainly, lines of forces and all, which whatever we do was all by him. But then there was this mechanical model for either could attempt for a lot of things. What they found is every time you wanted to introduce something, they have to make it more and more contrived. Therefore, their own simplicity was not there. This is very much like planetary motions also. Now we know everything goes like an elliptic orbit. You should really say that was not an easy thing to come arrive at. At the same time, people thought there was a lot of epicycles were there each because circle was the only thing people could understand. More and more epicycles could really explain these things, but the simplicity of understanding was not there. In the same way, here also you want to bring out a mechanical model, you have to make it more and more contrite. And uh, Maxwell was being person who got this dynamical theory of electromagnetic field. I'm sure many of you would have seen his treatise on electromagnetism, at least in library. Before that, he had his earlier edition was fully, yeah, a mechanical model of electromagnetism, which is now not in print. What Maxwell did was to give a mathematical formulation of what Faraday was trying to do. And what he did was he could reproduce all the known phenomenon about electricity and magnetism, and then he used only the Maxwell's Faraday's lines of forces, he eliminated completely a mechanical model at all, and he could go beyond the electromagnetic model. He could predict that electromagnetic waves are there, and electricity and magnetism were unified as one thing. Wave solution is possible, and the most important thing is displacement current. What we learn, we try to prove in two lines. Okay, at that time it was not at all a very obvious thing. In fact, this electromagnetism was very difficult to understand both for physicists and for mathematicians at that time, mathematical physicists. Physicists found that his mathematics was very complicated. Mathematicians found his physics was too abstract, things which we don't see. They are trying to bring in. The difficulty of mathematical formulation is we should know that whatever we learn using a vector and putting an arrow over that, all these things was developed by Gibbs only in 1900. Until then, this was not known. When Maxwell wrote his displacement current and sign cancelling all these, and then now you prove in two lines these things, But at that time, many terms were all cancelling each other, was completely a very miraculous. So, I think Boltzmann or somebody said there's an aura of miracle in this cancellation of displacement current. Okay, that was a very big change in that. And the very important thing is that primary constituent of the universe or fields was very difficult to come by for the physicists of Maxwell's generation. This is an article by Dyson. I don't know if anybody has not seen it. I would urge you to see it. I mean, he tells why is Maxwell theory sort of difficult. He goes with historically. I mean, what was the thing which went on? And Einstein, on one later date, he in the context of Maxwell's centenary or something, he makes this statement that since Maxwell time, physical reality has been thought of as represented by continuous fields, not capable of mechanical interpretation. This change of reality is the most profound and the most fruitful that physics has experienced since the time of Newton. Thing is that right now we have all right from the 9th class and all we have been learning the fields. We have been introduced to electric field and all, right? Possibly if you go for IIT coaching, you might be learning it in UKG, LKG, or pre-primary also, right? You'll be learning electromagnetic fields and all. But nowhere we try to accept it what it is, right? It was some kind of the fact that it is difficult to understand was not understood. Even as a student, I never felt that it is something very weird. How it can happen was never sort of understood. Okay? But that's because we have been brainwashed into believing that's what it is and accepting that. Now, therefore, this field concept was something which has to be developed. Now we have to understand what is mean by a field. What is the definition of a field? Field, actually, we have to think of it as a system with a finite, as a system with infinite degree of freedom. For particles, it is always a system with a finite degree of freedom. If you take a simple pendulum or double pendulum and all, it has 1 or 2 degrees of freedom. Fields means that's a one-line definition of this. To understand that, we can even take an example of an n-coupled oscillator, right? Which is what I have shown there. Okay, there is a there is this n-coupled oscillator. It has n degree of freedom because there are n oscillators are there. Now we can take these n to n oscillators with a is a distance between the equilibrium point. The total length is n. Now this is a finite degree of freedom because that's a number of degrees of freedom are n. Now one can go from here to a continuous system by the process which is to take n goes to infinity limit and the a goes to 0 such that L equal to L is finite. This again is standard mathematical things which I'm sure all of you would have studied. You would get a wave equation, then you get these vibrating strings. Now in these vibrating strings, what are the degrees of freedom? The degree of freedom is a displacement. Then where displacement, where at each point in space there is a displacement. How many points in space are there? There are infinite number of points are there. Therefore, it is a system with infinite degree of freedom. The fact that y is the degree of freedom, right? Y at every value of x at a given time is a degree of freedom, right? Time is still fixed at a given time. How many? What is to know the state of a system? I should tell displacement for all the x. That is the initial configuration. And that is what a given time what it is going to be infinite because x is infinite. Y is not infinite. Y is finite. Right? Y is a degree of freedom. And now these two can be mathematically related to each other. But then, which means that the parameters of this theory must also be related. Okay? The parameters of oscillators are going to be the mass of the oscillator, spring constant, the number of oscillators and all. If you look at a vibrating string, the thing is going to be linear density, string tension and all, and the wave velocity will be related to those things. Okay, when we do this limit, right, I have to take a goes to 0, right, one question which can come is linear mass density has to be separately defined. Okay, if a goes to 0, won't the linear mass density will be diverging? I'm not going to answer this question. Right? I mean, by answering this question, you would learn by this example and learning to answer this question. You will learn one very deep problem of field theory, which I will allude at the end. Actually, answer this is in the reference which I will give at the end. So, in the same way, electromagnetic fields are also dynamical system with a finite degrees of freedom, because the value of electric field is a finite number. At x at every point is a number of x is going to be infinite. Therefore, this is a system. Now we can ask how real are fields. What do I mean by real? So suppose I take this object. Right? Is this real? Why do you say it's real? Of course, one thing you may say is I'm seeing it. Right? I'll switch off all the lights. Then you won't say it. Is this real? Right? Is it still real, right? Just because you're seeing it, you're not going to say it's not real. Then what actually makes it a real? One way is I can make it real is I can throw it on you and you would feel the pain, right? Why it causes pain? Then you would say, yes, something real is there, right? What causes pain? Because this object has velocity, momentum, energy, angular momentum, all these parameters are there, okay? And therefore, anything which carries that, shouldn't it be also be as real as this thing is? You all know Maxwell's equation tells you that there are, associated with a field, there is a field for a given configuration. There is energy associated with that. There is a momentum associated with that. There's angular momentum associated with that. Okay? So therefore, shouldn't it be as real as this object? Okay? Though we don't see it. Second thing is, only difference is that here for this object, I can say where is it? I can say it is here. If you ask where is field, it is something spread out everywhere. Right? It is not localized at a given region. It is spread out everywhere. That is a basic difference from that. But still, it has all the qualities which a material particle it has. It can cause all the effects. If I sit in the sun, electromagnetic radiation, right, is again a field which comes and hits my skin. I get hot. Okay? All of them, it tells you that same way any other object can do that. Therefore, these fields are as real as any other objects are there. So we have to give certain sense of reality to it. So these are all I'm treating as a classical theory. So when you do this, you can write it in two ways. You can understand it as a classical, generalizing the classical mechanics of a Goldstein type. We can have everything goes through our fields, except that everything there is an infinite degree of freedom. Therefore, concept of a density will come. If you say Lagrangian will have a Lagrangian density, if you have Hamiltonian and density. This concept of a density will come when there is a continuum degree of freedom for a continuum system. Now we have to go for a quantization. There are two things when you do quantization. One can look at quantization of fields in a non-relativistic situation or on a relativistic situation. So I will first consider about a relativistic situation. where when you have relativity and quantum mechanics combined together, doing field is as of now only one inevitable way of doing physics in that. Therefore, I'll first go to the what is the meaning of a concept of a field when you go to quantizing that concept of a field. One is when you go to special relativity, there are things like energy and mass can get converted. Out of energy, we can get particles which can come out of, and that should be part of understood that process is. From a quantum mechanical point of view, this will appear as if there's a probability violation because earlier there was a thing like electron and positron. Right after some time it gets annihilated. Where is it gone? And earlier there was no photon. Suddenly two photons are coming. If you look at individually only of them, it will appear like a violation of non-relativistic quantum mechanics. But this is more an inadequacy of language. Instead, if you focus your language on occupation number, to say how many, right, a given number of things, how many people are occupying, then this change will see as a number of thing occupying has now shifted from 1 to 0. This is, this is has a fancy name as a second quantization, but we don't have to bother much about it because it's a very elementary and simple thing. See, suppose I want to give you the class of all the students, the BSc and MSc students, which they are all very different, like we have now. Then only way of characterizing is I have to tell where each student is. A student A is in class 1, student B is in class 2, right? That's the way I have to characterize. Suppose all the students are all clones of each other, very much like having identical particles here. Right? Then does it make sense to say student 1 is in class 1, student 2 in class 2? Does it make sense? No. What is the best way of telling? It's enough to say that for a given class, how many are occupying a given class? Isn't it? Isn't that a sufficient one? Right? That's a very, shall I say, common sense. Right? If you're given anything, why should you say that after all, they're all the same people? Right? Everything they are same. I mean, this analogy is to with identical particles of thing. Okay. Then what is the say? Does it make it makes no sense to no advantage to characterize it individually? So this, right, stating it as an occupation number is what is being called as a second quantization or all these buzzwords. So this one will give you a better way of handling. The student makes a pass from one class to the other class. It's like a transition from one to the other. Then occupation number from class to class 1 to class 2 has now sort of increased or things like that. Okay. If you present it in occupation number basis, these things will give you a better way of handling these things. And then the question is there anything else we have got experience we can just borrow? Right? In physics, when you go to a new thing, we should try to say whatever I know, I can use it to my advantage. Therefore, obviously, one thing, this now I'm going a bit above. I told people that 10th class students can understand to people, but it's not that I have to just. If you go to harmonic oscillator, right, there we have say, a similar situation that we have quantas of energy. There is a way that a given quanta of state can have some 10 quantas of photon, other state can have 11 quantas of photon. We have a formalism to make a transition from this one. Therefore, if you take that whole thing, behaves very much like a quantum of harmonic oscillator, and this system of particles where people are all identical particles and a given state have number of particles being, there is exactly a mathematical correspondence. For a given energy state in harmonic oscillator says there can be any number of quantas of energy it can have. In the same way, if you take both the identical bosons only, not for fermions, for a given state, there can be any number of identical bosons can occupy. Okay, this occupation number is similar to mathematically similar to the quantas which are going to happen. Then what is the best thing to do? You borrow the mathematical formalism of harmonic oscillator and then say use it there. Okay, that is the second quantization. That is what the field is going to do. Therefore, the mathematics of it is nothing more than a mathematics of harmonic oscillator. In fact, this harmonic oscillator comes in physics in so many cases. Even if you look at the string theory for the fundamental theory of gravity, they are also fundamentally they work with harmonic oscillator with in terms of creation annihilation operator. So if you understand that, you can almost learn all the subjects. Okay. Now, see, there are a few things that first we have to see what is the concept of field. But at the same time, we have also the concept of particles. What are the examples of particles? Electron, proton, neutron, those are the. Then, actually, historically, we got a concept of a field first, and then electromagnetic wave first. Then, with lot of trials and tribulations, we accepted photon as a concept. Historically, mankind. I mean, okay. So, photon was a concept which was emerged from the continuous theory of electromagnetic radiation to a photon, and that photon had all the entities of a particle. It had energy, momentum, and all. So they said if when something walks like a duck, quacks like a duck, then it better be a duck. So in the same way, they thought that that should also be a particle. So we identify photon as a particle. But then what is it initially when we first learned? Right? We learned the electromagnetic wave, the quantum of the energy of that one excitation, or excitation of electromagnetic field is a photon. Yes, and that has a concept of a particle. Now we also know independently there are a lot of particles are there. Electron is a particle, proton is a particle, Higgs boson is a particle, neutron is a particle. Right? Why can't we say that all these particles is also an excitation of a field? So when you ask this question, there are two reasons. Is there convenience? Is there advantage in doing that? Right? Not just for the heck of it, one should be able to do. Right? One should do is, can it explain something, known thing? Right? Is there an advantage in doing that? Okay? Or by not doing it that way, is it wrong? In fact, Bohr and Rosenfield, they showed that if you treat one as a particle, other as a field only, there can be a problem with the uncertainty principle. You can beat the uncertainty principle of particles if you don't do that enough. But okay, so there is the thing is now is that there are all the particles are there. Now what we do is we have to associate with every particle a field. No, I mean again take an analogy with photon. Photon, what did we do? We had a photon, then it is related to an electromagnetic field. Let's be clear. What is that relation mean? If you take the electromagnetic field thing energy, what is the lowest energy? Lowest energy when electric field will be zero, magnetic field zero, nothing is there. Then the lowest energy here will be correspondingly there is no photon for any momentum state. Absolutely no photon, right? Number of photons occupation number of photons for every state is 0, 0, 0, 0. Right? That is vacuum. If that is vacuum, small excitation having one photon is like a small excitation of the field. In that sense, the particle is an excitation of the field, right? And a vacuum is something where there are no particles in it. If that case, what we have to do is you must have a field associated with the particle, and the field must some stage characterize all the nature of the particle. Electron and proton has a different mass, right, and different charge. Therefore, this field has to characterize it. Therefore, for every particle, there should be a unique field associated with it. Right? And the thing is that, I mean, this again, I should come back to the question which Newton asked. Okay, Newton was said in future there can be something, immaterial thing can come. He said for gravity because that was only thing known at the time. Now we say that all these forces are all interacting through the fields. Charged particle gives an electromagnetic field. Other particle feels that electromagnetic field. So therefore, there is no invisible hand there. Right? There is no action at a distance. Right? It is like when I say if this moves, there is a small wire which is behind this. If I move this, that is moving. Therefore, you would say that's not a big deal. Okay? Fields have removed that thing. Therefore, now we understand that all fields come through the field interaction. And the main point is when you go to the high energy physics, where you have to marry relativity and quantum mechanics, you have a field concept is an inevitable thing. It's an inevitable. It's a compulsion, not a convenience. When you do second quantization for a non-relativistic system, it is convenience. If you do second quantization, it makes algebra and all much easier to handle. If you can as well work with the first quantization, which will be more messy. Whereas when you do quantum here, there's a difference is there. In fact, I mean that difference also is some discussion somebody wants I can explain. Now, when you learn quantum mechanics, first chapter we learn is postulates. So we should ask first thing: are there any? What is the difference when you go from postulates of quantum mechanics to postulates to quantum theory of fields? See, what we are doing is quantum theory of particles is what is combined as a quantum mechanics. Quantum theory of fields is is abbreviated to quantum field theory. Okay. So particles and fields are to be understood differently, like particles and waves. That particle is here, wave is there everywhere. Okay, that we should define. Given that, so what are the changes in the postulates of quantum mechanics? Once you go to the quantum theory of fields, answer is there is no change. In fact, even for a relativistic quantum mechanics, even in relativistic quantum field theory, there is an analog of Schrodinger field, Schrodinger equation, like something like dou psi by dou t is h psi, where h is a relativistic Hamiltonian of a relativistic theory. Such a Schrodinger equation exists. Okay, but what you do with that is depends on your convenience. If you want to apply WKB approximation, or if you want to do a variational method, I know in quantum mechanics, can I not apply it for fields? Yes, this method will be very useful. Feynman has worked a lot on these things. So he wanted to give a wave functional of quantum chromodynamics and all. Therefore, the first thing is many students have this difficulty of thinking that quantum mechanics of particles and quantum field theory are completely separated. So I want to give them the thing is that all of them exist. Okay, what you use for your particular purpose, we have to have a different techniques for each of them. Okay, if you say my purpose is something, find the Cartesian cross section or something, then you have to have a different methodology of doing it. That's the first thing. Then, in fact, one thing one can show is that if you have relativity and quantum mechanics, just to tell you that in relativity, it's a space-like, time-like, and light-like separations are there. And space-like separation means if there is a velocity greater than the velocity of light, and relativity also tells you the maximum speed must be velocity of light. Given these kind of things, for those who have not heard, it's a velocity of light introduction to relativity. So we should be very clear that there should not be a situation that there is amplitude for a particle to go with a velocity greater than the velocity of light, because you want to include relativity, but you are having something that should not happen. But actually, if you have only relativity and quantum mechanics of particles only, that is process will be there. There is an amplitude for a particle here. Find the transition amplitude of particle here to be found in a space-like region is going to be a non-zero number. Strictly, it should be zero. Right? It should be a non-zero. If that happens, then there is something wrong. So that happens if you have only quantum mechanics of quantum mechanics, relativity, and particles only. Okay, and this and one more thing. I mean, these things I just want to give difference. And one more thing is that when you do quantum mechanics, if we have observables, again they must be Hermitian. But one thing is that in quantum mechanics, we have only observables. It just depends on time. I mean, they don't position itself is an operator. Whereas once you do quantum field theory, like electric field or a magnetic field, now in quantum physics there are no operators. Okay, these are operators. Now they depend on a region. Okay, therefore the first thing is that observables are are called local observables. What does the word local mean? Local means it's a function of a space-time. Right? It's a local function, right? Which means at this point in space-time, electric field has certain value. At this point in space-time, it has another value. Okay, this operator and this observables are different observables because it is here, right? It is there. These are two different observables. Okay. Now we can ask this point in the space-time here and the space-time can be light-like separated, time-like separated, or a space-like separated. Okay, anything can happen. Now, one thing, quantum mechanics, independent of all these things, teaches us if two operators do not commute, right, which means measurement of one disturbs the measurement of the other, right? That is the first thing we learn. Okay. Therefore, if you are right, secondly, relativity tells you that there should not be any velocity greater than light, right? That signals cannot go faster than the light. This is the second quantum relativity. You know, we are trying to marry both of them. So we have local observables which depends on a space-time point here, another observable which depends on a space-time point here. You find mathematically a commutator between them, right? Especially when the 2 points are space-like separated. Okay. Suppose this commutator happens to be non-zero. Okay. Then what does it mean? When I measure this observable, right, the measurement of the other observable gets affected. Okay, which means that there should be some faster than light signal which must be happening. Okay, that we should not want it to happen. Therefore, only ways I want to impose this as a condition. Right? I'm doing a relativistic field theory, it better obey relativity. Okay, and also I should bring quantum mechanics. Therefore, it should also obey the quantum mechanics principle. Right? I don't want to tamper either quantum mechanics or relativity. Only way I can do is to say that measurement of one should not affect the measurement of the other. The simple way is take that you demand as a postulate. You demand that observables at a space like separated, they must always be commuting. Right? You put that as a condition on it. Right? Therefore, I mean, whether see one can ask this question. Okay, you all know at a microscopic theory how it can happen or not. Right? This is also related to something called a causality. Causality is going to mean everything has a cause and effect. Cause should happen first and effect should happen later. Okay, that is the first thing we try to do. We expect, right? If the world is not like that, world will be very weird. If effect comes first and cause comes later, we can have children born first before parents are born. So these kind of weird things cannot happen. But we can ask, how do you know many of these things are going to hold at a microscopic scale? We don't know. So we'll postulate like this, and the consequence we get, it should agree with the physics. Right? That's what. So this is imposed as a condition. This is also called technically as a macro causality. Observables must commute at a local. So that's a new thing which comes. Field theory says it should be local. Quantum mechanics says it should commute, and space-like says relativity. Right? For each of these things, I have taken into account. Now, I started the lecture by asking with Aristotle and this. I have to link with that. I have to ask why things are the way they are. How much quantum field theory is able to answer that question? That is what I want to answer. Okay. Actually, the first question is, I wrote in Cochin, not Sivas, and this was prepared for a talking. So I can ask why an electron in Calcutta and why an electron in USA are identical. Right? Why these two particles are identical. And after all, even if you prepare a ball, right, it won't be exactly the same. You prepare in factory and all, right? This we don't expect it to be any way different, right? That's something which if somebody says, I don't get this result because this is based on electron you have prepared here in LHC, it will work not in India. You won't work. It will work only. It won't work in a third world countries. It will work only in a first world countries, right? We don't do that, right? All these particles are identical, right? Why is it? This is something we never asked the question. Now field theory says these exist because they are all excitations of the same field. Field is permeated everywhere. These are all excitations of the field. They better be same. Okay. First thing is, I said there is a causality problem. Right? There is propagation. When field theory is that in relativistic fields, that causality problem is completely eliminated. One can show that. How many reasons? Maybe my references I will give you for that. We all know that for every particle there is an antiparticle. Right? The electron has a positron, proton has antiproton. Right? And basic thing is that all of them, very important part, the masses will be exactly the same. Right? Particle and antiparticle must be exactly the same. As of now, we have been finding that to be exactly the same. Right? Again, you remember that experiment must tell. At some very small length scale, if you find particle and antiparticle, slight difference in the mass, right? Many field theory, everything has to be thrown out and we should go back to the blackboard. But as of now, we could find both of them to be. Why it is like that, right? So question I'm asking is, why is it like that? That again, field theory gives an answer. If you impose causality as a constraint, you would find inevitably particle and antiparticle mass must be the same. If there's slight mass difference, it will violate causality. Okay. Second is, and there is also the spin statistics connection is that all of you know that every particle is inborn with a spin which is different from orbital angular momentum, because orbital angular momentum can take any values. Right? I can give you a large energy, and orbital angular momentum can be different. Whereas spin I can't increase. Right? I can give arbitrarily high orbital angular momentum, whereas spin of the electron I can't change it from half to 3/2 or 2 and all. I can't change it. It is always born with that. But still, the total angular momentum is orbital plus spin. Right? One you can tamper with the way you want it, other one it is born with. Okay? But this combination is essential for other reasons. Okay? Now, what one finds experimentally, observationally, is that integer spin always obey a Bose statistics, which is that wave functions are symmetric in nature, and Fermi or spin hard half integer, half 3/2 and all obey a Fermi-Dirac statistics, which means the wave functions are antisymmetric. The physical consequence of that is dramatically different, completely different. But why is it like that? Why things are the way they are? Okay? That is just a postulate in a non-relativistic quantum mechanics. Whereas in field theory, there is not a thing. If you impose causality, that will pop out. You have no choice in that. Half integer thing must be anti-quantum thing and relay, and at least for integer spin one can show in completely unambiguously. May not be as rigorous for half integer spin. That if you impose causality, then if you keep the statistics arbitrary and impose causality, both statistics will mean the causality constraint will say only possibility has to be symmetric positive. I mean, wave function must commute or anti-commute. It is that changes into symmetry or anti-symmetry wave function. So this also it explains why things are the way they are. There's one more thing, right from our high school days, or perhaps as I said, nowadays in LKG or UKG days, that like charges repel and unlike charges attract. Why it is like that? We always lean it as if this is what nature is. Now, if you have a quantum field theory, it explains why like charges repel and why unlike charges attract. This happens because this repulsion and this force mechanism is mediated by a electromagnetic field. Electromagnetic field has certain excitations. These excitations have spin one part nature, right? Which is photon, which is +1 or -1 helicity, and this is an odd number. And the thing is, whenever an odd spin which is being exchanged, then between particle and particle, there is always be repulsion. Between particle and antiparticle, there is always be attraction. And that is a consequence of relativistic thing. One can show mathematically that you start from the scattering amplitude for this process. Look at a non-relativistic limit, you would uniquely get the correct signs, positive and free. Right? So if you do that, the difference is in a potential, what you get. Right? Sign of the potential tells you whether it's attractive or repulsive. Okay? That is really comes out by that. So this also explains why gravity. In fact, there's one question which I always like to ask, that gravity, all of you know, is the weakest of all the force. But why was that the first force to be discovered? If it's the weakest, I would have thought that it should have taken more time to discover. Like gravitational waves, it took a lot of time because it's a bit basically weak. But why gravity was the first? Because that was the first force to be discovered. Hey, I mean, about half an hour before, 15 minutes before tell, because I have not even come to 40% of my talk.
16 minutes.
Oh, sure. Maybe I will go. I will go to the velocity of. I will change my velocity. This happens because this one. This happens. Maybe I'm not going to answer that. You think about it. Then there are problems. These are all the nice thing in kinematically. Once you go, we are doing it in perturbation. Once you go in perturbation, there are serious problems with that. Amplitudes, there was infinities were there, which people did not know how to handle that. Then these three gentlemen, Feynman, Schwinger, and Tomonaga, they found escape recipe for saying that all the things can be absorbed by redefining the parameters. What is meant by a mass of the electron? What is meant by a charge? Right? These are all by redefining that. So that scheme was called as a renormalization scheme. And as I said, a good framework should also make a new prediction. So this one, Schwinger made a prediction that the gyromagnetic ratio of electron has to be different from the at the known existing value 2. And that prediction, theory and experiments agreed for a miraculous level. And in fact, that first change is what the Schwinger's 2. So this alpha by 2 pi is engraved in this point. So I mean, this there is a change in perspective of what is renormalization in these days. Now we understand that renormalization in those days was understood as way of removing infinities. Right? That is the purpose of renormalization, and therefore renormalization is identified. At least as a student, I thought that it has to do with removing infinities. Nowadays, people understand that renormalization, the process has to be done, whether there's divergence or not. Renormalization has to be done. If there is divergence, you can use it cleverly to get rid of the divergence. Right? That's what it is. And they even made a prediction. Coulomb's law has to have a prediction, field theoretic correction to it, lamp shift, which also agreed with experiments. Now I said so far, now I want to change gear and I want to come to the modern perspective on what field theory is. So I'll take what under 15 minutes, okay, for this modern perspective. So now I want to change gear. I am not going to talk anything about field theory. I'm going to talk entirely a different system. That system is called, it is a thing where all of you called a second order phase transition. It's a phase transition, water to liquid, making a change. That's a kind of a phase which is a change. So there is some things like a paramagnet to ferromagnet. All the spins are randomly aligned. For a particular temperature, it undergoes a change. So there is a second order phase. These are called a second order phase transition. So this phenomenon of second order phase transition and quantum field theory has a lot of things in common, and that helps to understand what is the field theory. The first thing is field. I mean here this I have to go a little bit advanced. I mean. What it means that near close to the phase transition point, there is a divergences. I mean there are things like a deviation from the normal at the different regions are correlated. For example, I do something, I tamper, making it deviate from the average by changing the magnetic field here. Some very far away region will also be able to understand that. So this is called a correlation, and this is characterized by something called a length of correlation, how much they get correlated, and that divergence. The basic thing is that this correlation length is a quantity which is a maximum distance. Until then, all the distances are there. Right? So correlation is a maximum distance to which it is correlated. From 0 up to maximum distance, all the correlation lengths are present in this. Quantum fields, right? Therefore, if you see that this is going to mean that there is a scale of all the length scales are there. Whereas if you go to in the same way, quantum field theory, fields also fluctuate about the vacuum, and the degrees of freedom are different things. I mean, so this part is a bit advanced than earlier. So, I mean, the thing which I always wonder is second. Everyone used to tell, second order phase transition is one of the very difficult problem which Wilson solved, and I always used to wonder what is so big deal about that problem. Why was it a very difficult problem to understand? So, why this problem is this second order phase transition close to the second transition temperature? Right? Understanding what happens is it's a separate talk to tell you what are the nuances of the universality and all these things. I will not going to get into that. The basic is that science so far development happened because there is a miracle which has happened. The miracle is that science at a different length scales, right? They all decoupled. What do I understand? What do I mean by that statement? Suppose you consider a water wave. Okay? I can study water wave. I can study water wave at a meter scale. To study at a meter scale, what is the way I describe? I will take density, pressure, and things like that. Then I will write some Navier-Stokes hydrodynamic equation. That's a way of solving that. Okay. Now instead of studying at a meter scale, I want to study at a micron scale. Now I can't use density and rate. Those are not a relevant degree of freedom. What will be the degree of freedom? I have to use molecular level of parameters. Okay, I have to treat water as a molecule. Okay, now and then if you want to do at an angstrom unit, I want to look at, then I have to treat not as a molecule like an atom. Now if you want to say I don't want as atom, I want to look at Fermi scale, then I should look at it as a nuclear physics. You say no, I'm not even introduced the Fermi scale. I want to look at it like a Planck scale. Then I have to wait for a quantum theory of gravity to be discovered, right? And that is what I should use. Now, the thing is that to understand the fluid mechanical description, right, do I have to wait for the description after all the earlier levels? If I have to do that, I have to know. So, I have to know what happens at a molecular level, and to know molecular level, I should know what happens at atomic level. To know what happens at atomic level, I will know what happens at this level. And finally, if you keep on doing it, I should wait for the quantum gravity to be discovered before I even be able to understand what is happening in a matter wave. In a water wave, just as a fluid mechanics description, I cannot do that. Fortunately, that did not happen. Therefore, it is easy to do. The science has progressed. If that has not happened, even Newton and all would not have been able to understand physics, right? To understand the viscous force, a satellite and all, he has to say, I'll wait for quantum gravity to be discovered, right? And then I will try to solve, and possibly he will do something else. Okay, so they did not happen. This is a miracle I wanted to say. Physics at different scales all decouple. Now the question is, suppose they didn't decouple, what will I do? Why it decoupled? Because there are different length scales are there in the problem. Each of them I am able to treat. The problem with the second order phase transition and quantum field theory is there is no particular length scales. There are length scales at all the length scales are there. Therefore, I don't know how to separate them. But that is actually a problem. What is the problem which is not seen at a field theory at a pre-particle level? The problem of interacting quantum field theory shows up this problem. what is renormalization, what is all of them, as its deeper region that there are degrees of freedom, they are coupled at all length scales. Yeah? So once all length scales problem is there, that's a problem which is shared by continuous phase transition close to the critical point and a quantum field theory. So how do you handle that? So this was the idea which was first, the problem was solved by Wilson. The basic idea is that, see, I have to understand word fluctuations. To put a simple way, fluctuation means it's something deviation from the normal. See, suppose, if there is some curfew in one place because of some reason, right? There is deviation from the average. Okay, there is some curfew or maybe some problem is there in some region. Then smoothly it is going. There is some thing. Then we will see that. So like that deviation, these fluctuations are locally coupled, which means a fluctuation here first interacts with the fluctuation there. That fluctuation interacts with this one. These are locally coupled with each other. It's not that from here just goes to and talks with something far away. Right? They are locally coupled. That's an observation, right? Then there can be effect that these fluctuations slowly can be. These are details. I think I may not want to get into it now. So basically, is that okay? These are last two slides. So basically, so this slide and the next slide is a bit for a bit advanced one. So what we are having is that in that process, says some strength, strength can increase or decrease, and so this kind of a understanding of renormalization group in the context of a continuous phase transition gave some terminologies like relevant coupling, irrelevant coupling, or marginal coupling and all. Now what people understand is that whatever earlier quantum field theory people understood as a theory which was a renormalizable theory, non-renormalizable theory, or these are right, or what was called a super renormalizable theory. These are all has a counterpart definition in statistical mechanics. And now the present understanding is that every field theory has certain energy scale beyond which we don't know what are the things which are happening. Right? That energy scale is given by experimentalists, right? But then we have to just say beyond going that, which we have to make some changes. We have to make a prediction. That prediction agrees with it. Then we buy. Okay, that is a change is a right kind of a thing. So and therefore there should be a cutoff scale, which gives you a level of our ignorance. Yeah? And then we also have an accessible energy scale in which we are going to work. Now, the earlier people try to say that the theories have to be renormalizable. If they are not, the problem will be you will be ending up a theory where you have to have an infinite number of terms. If there are infinite number of terms, I don't know how to handle them. Right? Therefore, we'll say let us drop such theories, and then this has to be thrown out. Now, however, people has a change in conception that even though the infinite terms are there, but after all, you are going to make any measurement or observation only with certain energy precision, at certain level of accuracy. If you say my experiment has X% of accuracy, then you keep only in terms of that level of accuracy, then you leave that systematically. Right? So that's a kind of a change in perception of what renormalization group has taught us. So to understand field theory as an effective description of the nature below a cutoff scale. Cutoff scale is something which is so which is what gives you some limit of our ignorance. We know that none of even quantum electrodynamics, which explains everything, we know that it is not going to expect to be working to Planck scale or beyond Planck scale, because if it is works for infinity energy, then we know that is not going to happen really, because before that standard model interaction will take place. Before that, then the weak interaction, strong interaction, so many things are going to take place. Your Lagrangian does not have all these things. You don't expect it to work much beyond that. Right? Before that, experimental other phenomena are going to come and take part in it. So now we understand all these things are going to be part of a bigger theory. So this is what is a different approach. This is the same thing came up by Weinberg, which is this again, actually I'm taken from his book. So renormalizability is not a fundamental physical requirement. We now understand how quantum field theory works. It is only effective field theory. It's a description valid at a low energy. Because low energy means, compared with some Planck scale or beyond Planck scale, it's a low energy, but it's still high energy from energy physics point of view, right? Or like high or low depends on in comparison, right? Compared with Adani, I may be poor. Compared with some beggar, I may be a rich person. So scales come in comparison. So what is how to construct such a theory? He just says nothing more. It's actually not a. It's a way traditionally one has been doing. Right? You first identify the degrees of freedom. Right? If you want to at the micron scale, 1 meter scale, the degrees of freedom are going to be only density, pressure, and things like that. These are the degrees of freedom. Then write down what are the symmetries on those theories are there. Write down some effective, some most general theory consistent with this thing, right? And then whatever you do, then you try to understand what are the consequences by studying the effects of this theory. Okay? If you do that, you can try to get all these results. That is the spirit of effective field theory. In fact, one can show why skylight is blue, because we know the Rayleigh scattering. The way one does is you really take charge particle, right, electromagnetic wave and a particle, they interact, then you calculate a cross section, then there is a k⁴ type of cross section goes as it, right? So those kind of a thing, we'll say that, oh, that's what it explains why you think, right? Without these things, if you want to do effective thing, what we have to identify, we have to say atmosphere. What are the things it has? It is made up of argon, nitrogen, and argon and all. What are the typical size of nitrogen, right? And then what are the things it is going electromagnetic wave? What is the typical optical frequency? It has this much wavelength. Now, what is the typical size of a say atoms in this nitrogen atom? Right? That they are the maximum. Right? Typical size is this much. What is the wave which is in typical size is this much? Okay, in this wave, this is not going to see all the details. Okay, it's just going to see. Now you treat this as a scalar field and this as electromagnetic field. Write some most general Lagrangian, keeping only these parameters into account. Okay, which is just going to be scalar field, real scalar field, because electromagnetic wave is not going to see the internal structure of it because the wavelength is much bigger than this one. And you write the most general Lagrangian with this physical thing, then one line you would get a pro thing that Rayleigh scattering should go as this one. It explain, So that's the way one can try to do. And these things also, I mean, the next page is the reference for all these things. In the reference, all these things have been done. The reference is an advertisement. So I have written a textbook on quantum field theory. So there, every statement I have made is all explained. Why, how causality is removed, how spin statistics works, and everything, case by cases, everything. In fact, earlier I even had every section, but then I felt it is more advertisement, it doesn't look nice. So I removed all these things. So this is an advertisement of the book where, right? So I want to bring field theory as a modern understanding of this field theory, how field theory works. So this comes to an answer to this question. I don't know that. This is what I asked. How effective field theory is now, right? No, field theories are only an effective theories. So, just how effective the word is now, only effective theories. So I'll stop with this. Maybe answer. Happy to take questions.
So you mentioned the result by Bohr and Rosenfeld.
Yeah.
What is the actual result?
Actually, I forgot. I mean, if you treat electromagnetic field as a field and don't assume causality, then or don't treat them as a field, actually you can sort of beat until you can overcome uncertainty principle of particles.
In photon.
Yeah, treating as photon, that one. A photon, you see, the question is, should you treat photon as a field or not? Yeah, let me see. I know this is there in this quantum field theory book, right?
Quantum mechanics book.
Quantum mechanics book, right? Because as I was telling, suddenly it just came. It's not planned for it. So this is basically to tell you there's a requirement for fields. If you have to treat field as a particle, right? Okay. If you treat also like this as just as a field without as a quantum field, then you can overcome uncertainty principle of physics. That you can measure quantum position and momentum of another particle with which this interacts.
Okay.
Right? With which this interacts, that one can be understood if you don't read it. But this is modulo my understanding, right? So any of you can read Gottfried's book on quantum mechanics. Gottfried and Bohr.
That's the new edition. Original is only good.
Yeah.
That's an online question.
Yeah. Online. Oh, somebody is asking.
There is a question from an online.
Yeah, sure. In fact, I should tell maybe after this question, the Weinberg has also completely changed his opinion of when he got a Nobel Prize in his Nobel Prize acceptance lecture. He said renunciation is a very important criteria that among the many theories it is able to tell you that this theory is a very successful one, and that is what his perception was in his Nobel acceptance speech. Later he gave in his book he says that renunciation is not a fundamental criteria. Right, so that is what he has said in his book. He says. In fact, there is a very nice article. It is there in archives, which is he gave a talk about quantum field theory. What is
quantum field
what
theory?
Is quantum? What did we think it was? What is quantum field theory, and what did we think it is? My book refers to that. That was, in fact, when I first read that without knowing his book, I was completely stunned. It was something like a. Yeah, what was the question?
What is the question?
Somebody was asking.
No.
Online, that's what somebody was asking, right? That's
no,
what.
there's no question.
Is there any question?
Hello, if there are any questions in the online Google.
I have asked them.
Oh. So field theory is so that Weinberg has made a sort of a changing. In fact, but then recently I also heard a talk by Britain on Weinberg's 100th after his 1 year after he died. He gave a talk on Weinberg. So there he gave Weinberg's changing perception on non-field theory. But
There is a question from
Yeah.
Professor Banerjee.
yeah.
Professor Banerjee has a question.
Sir,
Oh.
Behind you.
Where should I?
Behind you.
no.
No, this way.
From Professor Banerjee.
Oh, you are. Yeah.
No, I just want to say that if for the in the case of non-linear field theory, I mean the spin statistics connection perhaps does not hold.
That's not cold. I mean,
So
there's no need to prove.
No need to,
No need to prove.
actually
Yeah, when people tried proving it, I don't know how successful.
No,
Yes.
it's not such.
Successful. Yes.
And the other point is you have given pictures of many people. But here you are coming at Bose, no picture of Sukhan Bose, and you have mentioned about indistinguishability, occupation, number. All this has come from S.N.
See, actually, I can tell you.
And even the
he
first
must
appointee
be
of
given.
SN was
Yeah,
He
given.
must be given. You don't let me. Europeans and Americans, this Weinberg, Dasher, Feynman, whoever he is, they never accept the contribution of Indians. Never. And one after they won Nobel Prize, they have denied.
Okay.
And not just Bose.
So I'll tell you
I
the
mean, there
reason.
is a J.C. Bose. There is a Enaki Chande, George Sudarshan. Poor fellow, he's shouting and shouting. And his cup of tea, at the breakfast, he was taking his cup of tea. The announcement, Roy Glover is getting the Nobel Prize. This poor fellow in the cup fell and he burned his leg. And the 8 Nobel Prize winners giving a note of dissension to the Nobel Committee. So what are you doing this? At least by giving the share. You are talking about all these diagonal, this thing and that.
No, I see. I didn't have.
No, Sivakumar,
Yeah.
I'm not going to spare you. You are my own colleague.
No, let me tell you. The problem partly is this talk. I'm just using the word transparency.
No, that is not.
No, sir.
Even for others, the point is.
Certainly.
You see,
Maybe I see. I should have made historically lot more photos.
No.
I did only for maybe
you
single
see,
photo.
the fundamental, Bose is the most fundamental contribution, the last of the 4 great papers on quantum mechanics, Brand Prize, and it is the paper which makes the transition to quantum field theory. It does it. I mean, just because a poor man is working from the Dhaka and nobody is there. To
Yeah,
show
maybe I
him.
should put lot more. Yeah, photos.
I think you
I
should
will correct
give
it.
SN goes at least.
Okay, I will correct. I will correct it.
At least this
Yeah.
one. Others are
Yeah,
not
yeah,
that
yeah,
possible.
Yeah, certainly I will correct it.
No, Hey, you are my close friend. I just.
Yeah, you tell me. You have liberty to tell. You have
And
liberty to tell.
your life started here.
Yeah.
With this Sunandan, he's introducing. He was there, lecturer there here. Hey, SL he never mentioned. Then he was the
That's why I
first
told
person
myself.
along with me.
Yeah, no, I told myself, I tell even yesterday in Presidency University, I introduced myself to say that I was the first person to come to.
Yeah, we are very happy, no? That Ashok Chatterjee was also there.
So yeah, so even yesterday I introduced myself only as saying that, so coming back, it's what you call.
Very nice
Yeah.
to see you back here.
So homecoming for.
Well, the talk is very nice, and I hope we have your book in our library and it's published by whom?
This one Annie publishers. Actually, I should please warn you, there are a hell of a lot of typos in it because they publishers, they just whatever I gave, he just published. I was expecting that he will send it for refereeing and check all these things. Nothing happened. So that was so I'm making corrections. So please forgive me. There are a lot of typos. Please bring it to my notice.
Actually, I have a copy of this book.
Oh.
I've purchased the book.
Oh,
And my student has also purchased a copy of this book.
very nice. But we have it in the library.
I will recommend the
So if you have it in the library, then everyone can.
Thanks for bringing it. I will correct it in future. No, I will just put all the Indian contributions.
It's a very
No,
nice
I will
talk.
put all the
and,
Indian contribution.
Yeah.
Specifically.
After all,
That is as a thing which we are supposed to do.
Yes.
And
also
also
in
I
your-
feel guilty.
And also your book maybe you can
Okay, I feel
update.
guilty.
You can also update your book in the revised
Yeah.
edition along with the typos.
it's such a nice talk, such a colorful one also. Definitely very nice. That's the good.
Yeah, sure.
It's not a big deal. I mean.
So, are there any more questions? Shweta, please.
So actually, what I understand is that the quantum field theory is entirely based on the Lorentz symmetry. So now Lorentz symmetry supports this one-rank tensor, second-rank tensor, and gravity is a second-rank tensor field. Now, in four-dimensional picture, it also supports, let's say, third-rank tensor field. But
Really?
I mean, it also supports third-rank tensor fields, let's say, within the four-dimensional setup, let's say. But we usually don't do the quantum field theory with high-rank tensor fields. I mean, even within the 4D domain. So, is
Why
there
is that?
any
Actually, yeah, that's a really good question. See, the thing is, what we do is first we identify the particles. We say that I want to display this particle, it has this spin, this nature and all. Then you say to this particle, it is quantum number. Say, if you say photon does not know whether it is a vector field or something. Right? It has only characteristics of mass and spin. Fields have entirely different one. For this particle, to which field you are associated, it's up to you to do that.
So it is more of an observation and input.
Yeah, then you know for everything it depends on a model. For a scalar field, right, you can describe in terms of second rank tensor, right? Massless, in fact, we have done lot of work on those things, right? So one can describe a massless particle in terms of this one. So we are associated only with the particles. The particle quantum numbers are in momentum space. Fields are in the physical space, right? So which one to do? It's your convenience. You can work with a quantum mechanics. See, instead of Dirac spinner, you can work with some other thing also. Like we don't know what it is. Electron it works. How do you know it works for quarks? Right? I mean, it seems to. I mean, if you assume quarks also described by a Dirac field, it seems to work. Therefore, we are working. Ultimately, choosing a field is a model. Right? That is a model. You see an observation of particles. You see for each particle what you observe is the field. That is a model. That model you should sort of choose it suitably. Yes. You can choose for some field you say third rank tensor can be playing a role. Then that goes that we don't know. For some inflator or something it may be useful. Right? There we can do. We are not saying it. These all of them are models. So in fact, with the 1% which I asked, why gravity was the first to be discovered despite being the weak. Has anyone answered? Okay. One more thing I should tell you the difference between fields and relativistic and non-relative fields, which have been brought out. One difference is you can define a number operator in coordinate space and momentum space. Those who know second quantization, you know you can write A dagger K, A K. Same way for a non-relativistic field, you can define psi dagger psi. Right? Psi dagger psi tells you number operator here, space. A dagger K tells you what is the momentum it has. Okay? Both of them are local operators. Whereas once you go to quantum field theory, you can define number operator in a momentum space. Have you seen any book mentioning what is the number operator in the coordinate space of the relativistic quantum field? So try to think about it. I'm not going to give answer. But for students exercise. And then if such a number of operator exists, see, for number of existing in coordinate space, you can ask the question, do they commute at a space like interval or not? Right? All these things one can just ask the question. But again, if such a thing exists or not, if it doesn't exist, in what form it exists?
So, sir, another question is that when suppose we are explaining the Hawking radiation, let's say, to some students or something, so we say that there is a vacuum fluctuations around the near the horizon, and the particle is coming out, and the antiparticle is going inside the horizon. So that becomes the virtual kind of an fluctuation becomes real. So we are perceiving some kind of radiation. So why we don't usually say that the antiparticle is coming out? I mean, is that antiparticle very rare?
This is actually no. One is certainly see that at that stage, what is particle antiparticle is also just the G plus and E minus. You can just I can as well. That stage you can change. I think that I don't think that deep.
I mean, is there any
See, one is we know that everywhere matter is predominant more than antiparticle. That is one thing we don't understand. I think that is diversified with the black hole. That is at a different level. Yes, speeds in the evidence that matter is predominant and antiparticle. Why they yes antiparticle. But this one may not be. I don't think it's a difference. They could have as well called it antiparticle is going.
Kind of
That you can go. And even when we learned the electron as a particle and you can as well say positron is a particle electron.
But they say that if an antiparticle is coming out, it has to readily be annihilated with the particle. So let's say that antiparticle cannot come out. It's an electron can be think of as a real particle coming out. So I have all this question.
I think at that stage, my understanding of I'm not an expert on backwards. I'm not gone through that in detail. Maybe others were not gone into that.
I mean,
Professor Banerjee can also.
Yeah,
why an antiparticle cannot come out?
So this person, what is that?
I mean,
My
why an
answer is that
antiparticle
there is no
cannot
difference.
go
Actually, that was called it.
At that level,
There is only a norm.
also you see even in talking original calculation, you see, point is there is as yet no foolproof derivation of the Hawking, which does not have some proof. There is no derivation, no. Whether you do it through Hawking's original calculation uses field theory in a regime where field theory may not hold.
So an
It may not hold at a space where Hawking has applied it. He has applied it.
So even if we forget about the horizon presence, let's say, so an antiparticle can roam freely. That there is no constraints on it from the fundamental theory.
No, they can roam free.
They can roam free.
As long as they don't meet other antiparticle. Only in the day-to-day life, they seem to be meeting a lot of electrons at that.
Yes,
In the free space, it will be going. Right? If you take on the free space and as long as they don't meet the antiparticles from the horizon, they can live. The lifetime is infinite. There's free.
Was it? Not all antiparticles, I'm sure.
No, yeah. I mean, from electrons,
yes.
I mean, depends on the interaction. Yeah, yeah. U plus has as much as different one.
Okay, so you can ask questions later on.
Yeah, and just
So are you visiting Calcutta for a
no, I say actually I came yesterday in residency university. I'm doing a talk on actually I'm running on physics training for students. I'm doing mostly physics education. Physics education for the BSc and MSc students.
for that reason?
Yeah, I just wanted to tell about that program yesterday to bring an awareness about that.
Where is that program?
I usually been running it. There are different places in India every year. I'm running.
This year also you are running.
This year also I am not got funds for this year, but every year we have different places.
You run it at Hyderabad?
No. Everything goes Hyderabad. It is my individual.